Hello everybody, good afternoon. Before we start the video, I would just like to share with you this website for the APIs for the finite element method. So basically the idea of this is to develop modular tools for the finite element method, which include many different type of elements. So at the moment we have shell element, full integration, reduced integration solid shell element, and the full integrated solid element already available. But we are also developing more finite elements and make them available. Simultaneously, we are developing a lot of finite element templates to use with our element libraries. So you can see some of them are just free as far as you subscribe the element that you need for your FEA analysis. You can get nonlinear implicit structural dynamics analysis for free, explicit time integration scheme, buckling analysis, model analysis, multi-point constraints where you can tie different parts. So all of that for free. There are other things we also have, but we are still working on them, but they will have a small subscription fee, like return mapping procedures for plasticity, crystal plasticity, isogeometric analysis, T-splines, nerves, these kind of things, contact analysis, which is important for modeling forging, sheet metal forming, rolling, structural optimization tools as well, J-integral for fractal mechanics. Now the way it works. So if you go, for example, to the full integrated shell element, so you have some introduction to the element with some benchmark analysis and tests comparisons. We also have a pre and post processor tool where you can visualize results and build your input files to do the simulations. So you can see that this API provides the strain displacement metrics, the stiffness metrics for linear analysis, and also provides other important FEA constructs that are fundamental for nonlinear continuum mechanic analysis, like the strain stresses, rotation of the axis, internal forces, geometrical stiffness metrics, and other things. So the way it works is, so we separated the subscription for individual and academic, like PhD students, postdocs. So the idea is, if they just need to use simulation with shell elements, why should they be paying for other elements and other FEA models that they will not need? So that is the main idea of this. So you can see it's quite cheap. We also have for business subscription, so depending on the business, so 1 year £99.9 is quite, for business, is quite a cheap price, right? So solid shell as well, so very quickly, so you have a lot of benchmark tests and simulations, similar things. So we have the graphical user interface, which we developed to use these APIs, which is so basically you can import, for example, input file from Abacus and then do the boundary conditions, materials, the properties, the loadings, do everything here and run the APIs directly from this graphical user interface. Okay, you can select node sets, element sets, visualize which sets by double clicking and seeing on the tree which sets you are seeing, the boundary conditions, loading, these kind of things. You can also visualize results. So this is a full wing model run with shell elements. You can see strains, displacements, stresses, everything. Yeah, so please, if you are interested, so just another thing, so the site address is macinmotion.com. So we have more than 25 years experience in academia developing the finite element technology. So all of these APIs we are providing a subscription. They were extensively tested and validated, and the results are really. I can just give you a quick one for you to compare. For example, on the solid shell size, if you go, for example, here, if you see these conversion studies for this. Okay, just a moment, maybe. Let me start with this. For this example, a twisted strip with different thickness, thin walled and thick structure. So we did run, so the API is this one, MRES API. So you can see it converges almost immediately. We compare with Abacus element, the classical one, C3D8, is very bad, but it's comprehensible because the C3D8 was not designed for bending, including bending in the 3D element. So Abacus has a better element, which is the C3D8i, the one in red. You can see it's much better behavior, but still our API still provides better results when compared with Abacus element. This is a different loading for that twist. So this is just an example to show. So we show here two of our APIs. One is the MRES, which includes bending capabilities on the element. The other is the classical 3D brick element, which is the one in black, which you can see in this example, which has a lot of bending and shear and torsion. You can see that MRES is almost perfect. Abacus C3D8i also works very well in this type of loading in this example. But you can see that C3D8 can give a very, very wrong answer, in fact, and I don't know if people are aware of this kind of situations. So this is a type of things we can provide. So just bear in mind that we are so all of these things that these finite element models for these many different problems, we have all of these implemented in Fortran. We are just basically coding this in C++, just transferring the code to C++, because C++ works better integrated with the graphical user interface, and that is and is easier to manage. Big FEA software is easier to manage software in C++ than in Fortran. So that's the reason why we are doing it, but we will soon have all of these procedures available, some for free, some for subscription, and we, of course, we provide full support on this matter. Please, if you want to reach to us, you can also go to the contact us. You have emails there at the bottom. You know now the address of the website. We'll be quite happy to discuss this with you in more detail. Thank you very much. Quadrilateral element. So you have an element of this type. In fact, let me do a bit better than this. We have an element like this. You have 4 nodes, one at each corner. So let's say this is node number 1, 2, 3, 4. Okay. And then what I'm going to do is I'm going to consider 2 coordinate systems here for this element. One is the global coordinate system, x, y. So let's make this in 2 dimensions, okay? For plane stress, I can put here. Plane stress, okay? Other formations are similar, but they involve more degrees of freedom eventually. But this is what we can do with the time we have.
in these sessions.
So you will apply central difference again here.
Sorry?
Central difference method again will be applied.
Yeah, we will apply. But before we go there, we need to calculate internal force factor and the mass metrics.
Oh, so you said it.
And then yeah, that's why we need to go into the element formulation, okay? To be able to calculate these things, we will need. Okay. Right. So the first thing is to define shape functions for this element. And in order to do that, I'm going to consider a coordinate system with origin at the center of this element. Coordinate system given by these parametric coordinates xi and eta. Okay. And then what I'm going to say is that in this coordinate system, xi and eta, node 1 will have coordinate xi minus 1, coordinate eta minus 1. Node 2 will have plus 1 in xi direction, minus 1 in the eta direction. So the first term is the xi, second term is eta, okay? Node 3 will have one, and node 4 minus 1 in xi direction and plus 1. Okay? So in this coordinate system, xi and eta, this element has always this shape, a perfect square, and the corners, the coordinates of the nodes at the corners, they are always minus 1 or plus 1, right? Always like this, okay? Now, if you have an element that is, for example, with this shape, not, sorry. Okay? Or squeeze or whatever. The shape functions will still be defined on this xi and eta coordinate system. So basically what we have to do is we have to do a mapping from this. We call this xi and eta the parametric domain. And then we'll have to do the mapping between the parametric domain and the physical domain, right? So this is the physical domain. Okay, so why do we do this? The reason why we do this is because when we are coding these elements in any FEA package software, like Avox, for example, we want to have the shape functions defined for one element configuration or geometry only. And that one is in this parametric domain because it's always the same between -1 and +1 in both directions. And then we can say, okay, the shape functions are going to be always the same. So shape functions for this parametric domain I'm going to say node 1 shape function is going to be 1/4 1 minus xi times 1 minus eta. Okay? We are going to see some properties of these shape functions. for node 2, shape functions of node 2 is going to be 1 over 4, 1 plus c times 1 minus eta. Shape function of node number 3 is going to be 1 over 4, 1 plus c, 1 plus eta, and for 1 over 4, 1 minus c, 1 plus eta. Okay? So with these shape functions, for example, if I want to know, for example, in this point here, imagine this point here with c and eta coordinates minus 1 over square root of 3 minus 1 over square root of 3. If I want to know, for example, my right?
Want to know where the details.
Yeah. If I want to know, for example, my coordinate x of that point, what I'll do is I'll do a summation from I equal to 1 to 4, because we have 4 nodes, okay, of the shape functions times the coordinates of each node, x coordinate of each node. Or if you want, I will say this is going to be equal to x is going to be equal to n1 times the x coordinate of node 1 plus n2 coordinate of node 2, n3 x3 plus n4 x4. Okay? And then the only thing I have to do is to replace in these shape functions my c and eta by the coordinates of this node, which is there. Okay? Now, why do we call this isoparametric element? Because we can interpolate. So basically, this is an interpolation, right? What I'm doing here is an interpolation, right? So I can interpolate, in fact, let me get this in the page. I can interpolate both the coordinates of any point on the element and also the displacements or rotations or the degrees of freedom if you want. Okay? So basically I can do this. So for plane stress, we are going to say each node will have we put here a more generic element. Come on. So each node will have a u and v, u1. So this is to displacement in the x direction of node 1, in the y direction, u2, v2, u3, v3, u4, v4. Okay. And then I can, as a parametric means, if I want to know the displacement, for example, in the u direction, that will be n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. Okay, so I can interpolate either the coordinates and the displacements using the same shape functions, okay, defined in the parametric domain, defined in this form that we have here, okay? Now, these shape functions, they have some properties which are important. I'm just going to show you. I'm going to show you some properties of these shape functions. So the first one, so let me try to, I don't want to be changing slide every time. First, let me make these guys smaller. So we have here some space to do something. Okay, now, first property I want to show you is summation of the shape functions is equal to 1. We call this the partition of unity. Okay? You can easily see that. For example, let's say instead of this point, I want to calculate summation of shape functions at point 1. Okay? So we can do something like this. At node 1, what you have is summation. I want to show you that this is equal to 1. So node 1, these are the coordinates here, right? -1 c, -1 eta. So if you replace in these shape functions, you will have n1 is going, so if I replace here c by -1, I have 1 plus 1 makes 2, and then 1 plus 1 here as well, because eta is -1, minus and minus becomes plus, c is -1, minus and minus becomes plus. So I have 2 times 2 is 4, 4 divided by 4 is 1. And 2, if I replace here c by -1, I will have 0, so 0 times anything is 0. And 3, same thing here, if I replace c by -1, I have 1 minus 1 is 0. Same thing here, 1 minus 1, 0. And n4, if I replace here eta by -1, I get 0, right? So the result of this summation is 1, right? So if I do the same for node 2, I also get node 1. You can try to do yourself. And so on, node 3, node 4. If I replace c and eta by this, coordinates of this point, -1 square root of 3, -1 square root of 3, you will conclude same thing, summation of all the shape functions equal to 1. Okay?
So it's always going to be equal to 1.
Sorry?
The c and eta is -1 and 1, and it's always going to be equal to 1. It would be the same if it's -2.
The summation of all shape function, yeah? Yeah, what was exactly the question?
So like depending on the shape, if it was -2 to 2, like if it was double the size,
No, but this is always between -1 and +1.
only for this.
Always. No, always. The parametric, when the shape function are defined in this parametric domain, always between -1 and +1.
They can't
Okay?
go outside that.
Always. But then, of course, the real, when you do a mesh, you don't have these perfect elements, right?
Yeah.
And they don't go from -1 to 1. So that's why we are going to do, I talk here about this mapping between these two coordinate systems. So we'll need to map or make a transformation from this parametric domain to the physical domain of the element. Okay? And in fact, I'm just about to do that. Okay, so let's do one thing now. So I can say that an increment in my x coordinate, I can obtain this by getting, chain rule, an increment in the x when I change my xi parametric domain times dxi, and I do the same in the eta direction, right? Oh, no, this is like this. Okay, I can do the same for the y direction. I can say this is going to be, that this should be partial derivatives, but it's okay. Okay. Now, why are we doing this? The reason why I'm doing this is because I can, in fact, put this in matricial form. I can say the x dy equal to this matrix, the x dxi, the x d eta, dy c, dy d eta, and this will multiply increment in the c direction, increment in the eta direction. Okay, so what does this allow me to do? This allow me to yeah, this thing allows me to do this. If there is an increment, or if there is a variation in my xi and eta parametric coordinates, if I multiply that variation with this matrix, which is Jacobian, then I can get, okay, I can write here variation in parametric domain. So if I multiply that variation in parametric domain by my Jacobian matrix, I can get my variation in the physical domain, which is really is a kind of the mapping I was saying, right? And the matrix that does that mapping between the parametric and physical domains is the Jacobian matrix, okay, which is, you are going to see, is going to be a very easy thing to calculate with these isoparametric elements.
We're gonna do this in MATLAB.
Sorry,
We'll do this in MATLAB.
we will do this in MATLAB, but first we need to understand a little bit and talk about this. Understand the theory, right? Otherwise, yeah, exactly, very good. Yeah, so this thing, how are we going to obtain this? Look how easy this thing is going to be. I told you that we can obtain the x coordinate by doing the multiplication of the shape functions with the coordinates at nodes. I can do this for x, I can do this for y, right? You agree with this? It's interpolation, right? And now look at this. What do I need to have in my Jacobian? Is the derivative. So I need to add the derivative, for example, derivative of x in order to see. So looking at this equation here on the right-hand side, this is going to be equal to summation. So I have a product here, shape functions time normal coordinates. So the normal coordinates, they are constants. Yeah. So basically, I only need to derive shape functions. So the shape function, don't forget, they depend on xi and eta, right? I need to derive now in order to xi, multiplied by the coordinates of the nodes, and I get my This is super easy to do in MATLAB, in implement computer, right? The summation, which you just do a for loop from 1 to 4, and you multiply the shape function by coordinates of the node, and you get this derivative. Yeah, we're going to do that. Same thing for y. Derivative of this guy in order to c, and for derivative in order to eta, copy this and change this quicker. Right. So derivative in order to eta, I just need to derive now in order to eta, right? Right? So one thing we can do these derivatives of shape functions. Let's bring the shape functions, these shape functions. Let's bring them to a new slide. Let's put them here. And let's do the derivative of n1 in order to c. The derivative of the first shape function, okay, this one here, in order to c. So it's going to be minus 1 over 4, 1 minus eta. You agree? Now derivative of n1 in order to eta, we can do that way, is going to be minus 1 over 4, 1 minus c. It's super easy. Derivative of the second, so this will become a little bit repetitive, but in order to c is going to be 1 over 4, 1 minus eta. In order to eta is going to be equal to minus 1 over 4, 1 plus c, right? So if I have any mistake, please let me know here. Derivative of the third shape function in order to c is 1 over 4, 1 plus, b3, yeah, 1 over 4, 1 plus c, right? And last one is the derivative of n4. So minus, right? 1 plus eta. And 1 over 4, 1 minus c, right? Okay, super easy. And now we just need to replace in our Jacobian. So what we can do is our Jacobian. So this Jacobian we can write, this is going to be summation from 1 to 4 of the ni in order to c, xi. The second one is going to be summation from 1 to 4 of derivative of the shape function in order now to eta times xi. in second row, we need to add summation I equal to 1 to 4 derivative of shape function in order to see. But now we'll multiply the y coordinates at each node. Okay. And the last one, derivative of the shape functions in order to eta times coordinate in the y direction at each node. Okay. Of course, if you are doing a 3D problem where you have a z coordinate, you will have a 3 by 3 exactly Jacobian, and you will need to have a derivative in order to coordinate in the z direction. But anyway, let's focus on our plane stress 2 dimensions now. Okay.
Sorry.
Yeah.
I have another question. That right now you're dealing with a square shape, right?
Mm.
How about the aerofoil when we come to that? How this because
No, in airfoil, I think we already discussed last week. You might not need to do this
okay, this is not
because you have your equation of motion, right? You will have a stiffness,
that is given.
yeah, and you have a mass.
Yeah, fixed mass.
Yeah. So what we are doing here is we are going to basically have the same thing here, a stiffness and a mass, but in the context of finite element analysis. And then we are going to go to the central difference method and do the time integration of this thing, right? Yeah.
Yeah.
So in your coursework, you will also have a stiffness and a mass, and the central difference method you need to use as well.
Start the equation.
But you will not have a mesh like this, right?
Mesh.
You don't have a mesh, right? In your, I don't think.
I mean, I went through it very quickly.
What do you say by mesh? I read it.
You don't know what is a mesh?
No, I know what the mesh. We have to mesh the airfoil.
You have a mesh for them.
Yes, and it changes over time by Flutter because we have to change it.
So if you have a mesh, then you have to do this. Yeah.
Because last week I understood, you would have.
Well, depends on the elements you are using in your mesh. I don't know. You need to check in your coursework which elements you have. Is what? Is shell elements, plate elements, is beam elements, is I don't know which elements you have.
Number of divisions define, number of divisions.
Yeah, you need to figure that out. Yeah.
The thing that we said last week, it was okay, k theta times theta k h times h. That was applied, central difference method, the process that we explained regarding the time, t minus 1. That makes sense. But this one, I can't figure it out because I read
You
it.
need to wait. We are just starting. We are going to have some conclusions at the end. You need to be more patient. If I give you the final thing, you will not understand anything, correct? So we need to go step by step for you to understand how these things work. Because then it will be much easier, in my opinion, of course, for you to implement or to transfer this to your course, right? If we go to straight away to the final thing, you will not understand anything, I think. Okay. Okay, this is Jacobian. Now, there's one thing we can do. Which is Jacobian is also used for another yeah. So let me do one thing very quickly. Now, Jacobian is also used for coordinate transformation between the parametric domain and the physical domain. How do we do that? Well, So this is, don't forget, this is my Jacobian matrix, J, we call it J. But I can invert this matrix, and then what I will have on this side. So basically what I'm saying is that I can obtain the variation on the parametric coordinate from the variation on the physical coordinates. And then this is going to be my J minus 1, the inverse of my Jacobian. And what I will have to do here is going to be dc dx, dc dy. Here I'm going to have the eta dx, the eta dy. Okay?
This must be negative from the diagonals.
No, this basically this, the reason why this is like this is because I can write like we did before, right? So if I multiply the first one, if I multiply the first row with this vector, right? This is what I get here, right?
The inverse from,
Yeah, the inverse we are going to calculate in MATLAB automatically.
okay. so
Yeah.
no worries.
Yeah, we will not worry now with the signal. It can be positive or negative. Yeah.
Is there should not be one over the determinant of that?
Sorry?
1 over the determinant for j to the power of -1 inverse of that magnitude.
Sorry.
It's not when you want to do the inverse, it's not 1 over the determinant times
Yeah,
the determinant.
yeah, but I didn't calculate the inverse of the matrix. I just put this matrix here by just
It's not
I just
absolutely
did it by just doing this, right? Now what we are going to do is we are going to build the Jacobian, implement these for loops to get Jacobian in MATLAB, and then we are going to ask MATLAB to invert the matrix for us.
So in fact, that second matrix that you put there, the second one, is just something that you did it yourself. That matrix is not a real thing. That inverse j to the power of -1 is just from yourself. It's not no real physics.
Yeah, this will be the inverse of Jacobian. Yeah.
Oh, at the end of the thing.
Yeah,
You,
yeah. Okay, and where are we going to use this inverse of this Jacobian? We are going to use, for example, if you want to calculate, imagine if you want to calculate the strain in the x direction, okay? We know that this is the derivative of the displacement u in order to x. And then we are going to say this is going to be equal to applying the chain rule of the derivative of u in order to c times the derivative of c in order to x plus the derivative of u in order to eta times the eta dx. Well, this dc dx, the eta dx, they are here somewhere. Dc dx is here in the inverse of Jacobian, right? The eta dx is here, right? Yeah. Now, what about the u dc? Well, look at this. The u dc is going to be equal to, this is the isoparametric approach. We just need to derive the shape function in order to c, which we already did, and multiply by the displacement at the nodes. Yeah? Du deta. Derivative of the shape functions now in order to eta times the displacement at each node. So we have everything. So we have this stuff in green we have all of it because we have the derivatives of shape functions. We have the displacement at nodes, which are our degrees of freedom. The stuff in red, circled in red there, they are taken from the inverse of Jacobian. Okay? So the procedure is going to be quite easy. We calculate Jacobian in MATLAB, do this for loop. We ask MATLAB to calculate the inverse. And then we use the terms in these positions of the inverse to transform. And the strain you get at the end, as you can see here, the strain you get at the end is in the physical coordinate system, is not in the parametric. So basically what we did here was a transformation of coordinates, right, between the parametric and the physical domain by just using Jacobian and its inverse.
And you love MATLAB coding.
Some MATLAB, not a lot. I think it's going to be less than yesterday.
Yeah.
Oh, yesterday, sorry.
Last week.
Yeah. Well, we'll see. We'll see. But before we go to MATLAB, I would like to do a little bit numerical integration, okay? So look at this. Another advantage of this Jacobian is on the numerical integration. So you remember we did last week, for example, for the stiffness matrix, we need to calculate the integral in the volume of the element of this B matrix transpose times D times B, right? And we need to integrate this in the volume of the element, okay? Now, let's think about it. Plane stress, okay? So we are in two-dimensional plane, but the element will have a thickness, right? So I can say for plane stress, our plane stress element, I'm going to say my stiffness is going to be equal to the thickness of the element, which I'm going to assume is constant in the element, okay? One element has constant thickness. The rest becomes too complicated. Is okay? So if it's constant, I send outside, and then I will have to integrate double integral in the x and y direction, right, of my element. Area integral, right? So this double integral is a kind of integral in the area of my quadrilateral element, right? Is okay?
Right. So you want to do double integration in MATLAB as well?
Yeah, but we are going to do numerical integration, not analytical integration.
Well, for double.
Yeah, for the double integral, yeah. But before we continue, there is a problem with this integral here. So you guys want to guess what that problem is? In this double integral. So I'm doing integral in the x and y direction. Do you think that is a good way to do it? I mean, if you think on this, let's go to the first slide. Yeah, if you think on these two elements, one is a perfect element, always a square in the parametric domain, which I always know the limits of that integral, right? Between -1 plus 1, right? Always. The one at the bottom is an element in the physical domain, which can be squeezed or, distorted element, very irregular shapes, different shapes every time, right? Imagine a mesh, you do 1 million elements. How many different shapes do you have there? Yeah. So if you are going to do the integral in this physical domain, which basically corresponds for the element below at the bottom, you will need to be coding that integral for 1 million different elements or 10 million different elements. Can we do that? Of course not, right? So we need to do that integral in the parametric domain for the figure above. Why? Because that parametric domain is always a perfect square from -1 to +1. So I just code it one time. Yeah. So that's the problem of this integral here. So I need to for my stiffness, so we are calculating stiffness, but we are going to see for the internal force is going to be the same. So I'm going to do this from -1 to +1 in the x direction, -1 to +1 in the eta direction, integral of what? My bt dv. And now see the eta, my parametric coordinates, but I need to do something more here, which is the determinant of my Jacobian. Oh. Doesn't fit, just a moment, let me move this. So I need to have here the determinant of my Jacobian.
Sorry.
Yes.
Can I ask a question? My question is regarding the last week that you covered and this week, the difference. I remember it was, I think, in fact, the beginning of the 2 weeks ago. We had two nodes. Right now it became four. The only difference is this one. Right now you have a mesh, as you mentioned. What's the difference between the previous weeks, week 1 and 2, and this last one?
Previous weeks we are working on with a truss, sort of a strut element.
The three.
Yeah, when we introduce a related residuals. Now I'm doing a plane stress element. Okay, just to give you an idea. Okay, now you are in a 2D. For the truss element, we only use a one-dimensional shape function, right? Remember? So it was a shape function in one dimension. The strut element, it had two nodes.
Yes.
You had two shape functions and 1 and 2 in one direction only, right? Now this one, plane stress, the reason why I'm doing is because it is in 2 dimensions, right? And also I want to introduce numerical integration, this isoparametric coordinate system, which is ideally used in FEA. Okay. So it's not only plane stress elements that use this isoparametric approach we are doing here, this parametric domain and physical domain. 3D elements, hexagonal elements, the shell, plate elements, they all use this kind of approach, right? Because there's a huge advantage. For the numerical integration, we are going to see, like, we integrate in a perfect regular square, right? This is unique advantages for developing these FEA codes and put this in a computer, because we can just implement this for a regular element defined in parametric domain. And then you can do your mesh with many different shapes of the elements, and it will always work for any element, because we do the mapping between this physical domain where your elements are distorted to this parametric domain where your element is always a perfect square. Okay? That is the advantage of this thing. So I cannot tell you that with the strut element.
That one.
That's why I'm moving now to plane stress. Okay?
Yes, sir.
And also give you an idea that in a FEA code, you have many different types of elements, each element with their own formulation, right? This mathematical formulation we are seeing here to build the stiffness, to build the mass matrix, to build the internal force vector. Yeah. So we already talked about stiffness. We introduced that with the strut element previous weeks. But this week, this plane stress is better to introduce the mass matrix, which you will need for your central difference integration. Yeah,
yes, sir.
Your assignment. And also for the internal force vector is more, I'd say more generic, more standard approach. You'll hopefully you will see it better, right? And also for the numerical integration, you remember when we did the strut, we did this volume integral. We calculate the length of the strut. We multiply the length of the strut by the area of cross section. So we have the volume of our strut, right? So now we are doing a very different approach. We are doing an approach that works for any type of element. This isoparametric approach, and this numerical integration we are going to do works for any approach. Okay. All right. So now it is much better now, because look, the limits of our integrals, they are always between -1 + 1, always. Look, here in the physical domain, you can have an element that has a limit in the x that goes, for example, -10 to -5, and then another element, a second element where the x goes from, for example, 1 to 3. It can be changing the limits every time.
Yeah.
In the parametric domain, these limits are always the same, -1 plus 1, that's it. The only thing that really is different is this determinant of Jacobian. But it's perfectly fine. We calculate Jacobian. The determinant, so easy, isn't it?
The last slide.
Huh?
The last slide, we got it.
The last slide, we got it, yeah? So here in the last slide, the determinant of the Jacobian, if you want, I can very quickly. We can even ask MATLAB to calculate the determinant. Right? So if I put here the determinant of the Jacobian, this Jacobian is going to be equal to dx dx times dy d eta minus dy dx times dx theta, right?
Yeah.
Very easy, very simple to do. Now, we are not going to do this analytical integral, okay? The reason is you have, if you want to do the analytical integral of this thing, you have this bt db and determinant of j, which can be very complex to do this analytical integral. And then on top of that, when you implement this in a computer program, we don't do analytical stuff typically in computer, right? We do numerical approximations. So numerical integration, let's replace this analytical integral by a numerical integral, a numerical integration if you want. Let me write it here, numerical. So imagine we have okay. So let's see, here is the function we are integrating. Let's say it's our bt d b that j, okay? In the vertical axis, imagine this is a function like this. It doesn't matter, I just plot here a curve like this. So let's consider only one direction. So let's say, for example, this is my c direction. So this point here is going to be -1. And this one plus 1.0, okay? So this is 0. So the way I can integrate this thing is to calculate this point is -1 over square root of 3, and while this one is +1 square root of 3. So basically it works like this. I evaluate my function at this point. So this is my c, right? C variable, right? We call these points in red integration points. So I evaluate this I evaluate my function at this point and calculate. So basically what I do is I do a summation from 1 to 2, so in the x direction. So much, let me do this. So what I do is I calculate my BT C integration point 1 multiplied by my material matrix B, my matrix B. So I evaluate my function at this point. I calculate my determinant of Jacobian. At this point I, and I multiply this by a weight, which, if you want, is the width of this thing. Okay. So don't forget, the integral is the area below the curve. So when we do the analytical integral, we are looking for the area below the curve in blue. Right? In the numerical approach, so I calculate, so this is my C point 1, this is my point 2. So if you, this first term, if you look carefully, is the, maybe I can use a different color scheme. So my integration point number 1 is the one in red. My integration point number 2. So this is my WI. This is going to be my W double I. So if I add my BT now evaluated at my point number 2 times D times B times determinant of my Jacobian at point number 2 times Y2. So basically what I'm saying is the result of this is going to be equal to my stiffness matrix. Input like this. This is the analytical. Okay. So I think this slide, as it is like this, shows you well, in my opinion, of course, the numerical integration scheme. So look, we are aiming the curve in blue, the area below the curve in blue. We are aiming for that to be our analytical integral that will deliver our stiffness. We're going to replace this analytical integral with numerical integration, which in this case we consider 2 points in the x direction. And what do? We evaluate our BTDB at these 2 points and multiply BTDB by this, we call this weight function, which is well defined for the different types of numerical integration we have. And then if we do that, basically what we are doing is the area of this rectangle in red, and we are adding to the area of this rectangle in green. And you can see that if you consider overall, the difference between the analytical, the one in blue, and the numerical, the red and green, added together, in terms of the area below, it's not going to be very different because look, you have this bit here that is not in blue, but you are not considering this bit here in the blue as well, right? So one gives for the other, and you know, it's
If we have a political solution at the bottom,
yeah.
and it's an exact correct solution, why, if we have all those factors already, why would we want to do?
Yeah, that is the thing, but
We have all of those.
we don't have, right?
But we have the D matrix, the B matrix, the determinants, all of those.
Yeah, but this B matrix in the B matrix and the determinant of Jacobian, it will be different for every element.
Okay.
Right?
Yeah.
Because in physical domain, right? Because you can have distorted elements, different lengths of, for each element. So this will always be different. So if you are doing the analytical, you will have to do analytical integral of the function inside is always different for every element.
Yeah.
While this numerical one, because it's done in the parametric domain, is always done in a perfect square, right? You just need to do the BTDB, calculate this in these specific points at these coordinates, yeah, which are the integration points. This way, so this is full integration, that way. This is what we know as full integration. Let me put here. And for this full integration, you have the weights equal to 1.0. Okay.
In fact, that term doesn't exist. That's one to this one.
Sorry?
The W doesn't exist always because it's one for all of the points.
Yeah, it exists, but is equal to 1 for full integration, yes. But for example, one thing you see a lot in commercial software, reduced integration, right? So for reduced integration, what they do is, instead of 2 integration points like we have here, they only use 1 integration point. So let me see if I can clean up this thing. Oh. Let me just clean this, otherwise it'll be, because I cannot sketch the same blue curve exactly the same, so it's easier to delete this stuff, isn't it? Yeah. Also, you can take this to charge your brain a bit more. Okay, so reduced integration. The point we use is at the center of the element, this point here. So we calculate the function at this point. And the weight we use is 2.0. Okay? So basically in the reduced integration, you have only one BTDB. Right? And now, of course, you are going to have here reduced integration. And your weight is not one. In fact, this guy goes away. 2.0. Okay. There are other integration rules. So basically, this is the Gauss integration. So that's why you hear a lot of times Gauss points, right? Okay, you are not cooperating. So the Gauss points are these points. These points where we evaluate our functions, okay? Now you can understand better why. For example, when you go to FEA, the strains, the stresses, everything is calculated at the Gauss points. Why? Because we need to do always these integrals for the stiffness and internal forces. So we need to have, so don't forget this dB times the displacement vector is the strain, right? So we evaluate these B metrics always at the Gauss points. Why do we evaluate at Gauss points? Because we need to use the Gauss points to do the numerical integration. So we have these B metrics calculated at the Gauss points. And because we need the B metrics to calculate the strains, right? Yeah, don't forget that the strain is your B matrix times your displacement matrix with the degrees of freedom. Because we need the B matrix to calculate strains, and because we need to evaluate the B matrix at the Gauss points for numerical integration, the consequence is that our strains are also obtained at the Gauss point.
The P was the displacements.
These displacements. So D in case of our plane stress element is going to be our U1, V1, U2, V2, U3, V3, U4, V4. Okay.
Like how P?
B. B is the strain. We did this last week, right?
They just showed me.
Strain displacement. We did this for strut, but we need to have this for all elements. Basically, the name is very suggestive. Strain displacement says, okay, this is the displacement. I can get the strain from strain. So like I was saying, because we evaluate this B at the Gauss point, at the integration point, the strains will be at the integration point. And if you continue, your stresses is your from Hooke's law, right? Is the this is Hooke's law, right? Material matrix, which has the Young modulus Poisson ratio, right? Times the strain tensor, this gives you the stresses, right? So if I replace the strains now by my you can see why we have our stresses as well at the Gauss points, integration points. Because again, we need strain displacement matrix again to get our stresses. Okay.
That S1D is a displacement as well, capital D. Capital D.
No, this. Okay. When you know the Hooke's law is that, right? That relates the strains with stresses, right? So okay, so I suggest we do a break. What do you think? Before we, and then after the break, we go to MATLAB. Yeah? To implement this thing. Okay, so let me just